Hi, in this video we will study an important property of orthogonal bases. We will see that writing a vector as linear combinations of vectors of an orthogonal basis is very easy. We have explicit formula for these coefficients of this linear combination. Well, let me start with an example. In R2, I have this orthogonal basis is an orthogonal basis for R2 means what? Means that every vector can be uniquely written as linear combinations of these two. Now I want to write the vector W 1 as linear combination of, let's say this guy is V1, this one is V2, of V1 and V2. This is something that we have been doing in chapter 3. Well, how do we do this? Well, we are looking for scalars C1 such that, and a scalar C2 such that C1 times V1 plus C2 times V2 is equal to W. And then we write these things for the coordinates. We form a system of linear equation, we solve it and find values for C1, C2. That is for general basis. When your basis is orthogonal, you don't need to solve any system. What you do is, well, let me show you here, and then in general this will go the same way. Dot product this equation by V1. So you will have V1 dot C1 V1 plus C2 V2 equals to V1 dot W. Then, well, we know that this is C1 V1 dot V1 plus C2 V1 dot V2, and this is equal to V1 dot W. Very nice. But we know that the set is orthogonal, so this will be 0, and that will give me C1 V1 dot V1 is equal to V1 dot W. You know that this is a number, this is a number, and these are known. You just dot product V1 to itself and dot product it to W. These are two numbers. And what is unknown here is C1. So we can find C1 now by dividing V1 dot W by V1 dot V1. Well, in this case, this means that, well, dot product of 1, 2 and 1, 1, and here 1, 2 dot 1, 2, which will give us 3 over 5. You see, I'm not solving any system. I'm just taking this formula, and then C1 is given. You can do similar computation and you can find C2, which is equal to V2 dot W over V2 dot V2, and that is equal to what? Negative 2, 1 dot 1, 1 over negative 2, 1 dot negative 2, 1. And this will give us negative 2 plus 1 is negative 1. This will be 4 plus 1, which is 5. Well, very simple. Now you write 1, 1 is 3 over 5 times 1, 2 plus negative 1 over 5 times negative 2, 1. You may say, well, the amount of work you did here is almost the same thing as solving a system. Well, you're right if I didn't have this final formula here. What I showed you actually is a proof, and it works in general theorem. that says that let v1 up to vn be an orthogonal basis for Rn. Okay, and well, this cannot actually be any subset for W subset subspace of Rn. And well, for any vector in W, this is subspace. So any vector W in the subspace W can be written, this is nothing new, can be written as a unique linear combination of VI's. Well, it means that W is C1 V1 up to CK VK. So far, there's nothing new. This is what is new and what we showed up there. Here, the original set can only have K, yes. Here, Ci, any coefficient you want, I have a formula for that. You find dot product of Vi and W, the vector W, over V1 dot V1. And this formula is what makes it unique, that what makes it easier to compute. And this is for all i's from 1 to k. Compare it to the other bases. If you don't know the set is the basis is orthogonal, then you have to form the set of equations, a linear system, and solve it, and each time you will get different things. But when it is orthogonal basis, we have formula for each one of these coefficients. Let me paste an example here. Well, find the coordinates of W with respect to a basis, an orthogonal basis. So this basis is orthogonal. Well, I already checked it. Now I want to write W as C1 1 to negative 1, C2 negative 1 1, and C3 3 0 3. I don't need to form any system of linear equations. C1 is going to be V1 dot W, I'm calling this one V1, V2, and V3 over V1 dot V1. So in this case, well, it is 1 times negative 1 plus 2 times 2 plus negative 1 times 1 over 1 squared plus 2 squared plus negative 1 squared. So that's V1 dot V1. And well, when you compute this guy, this will be 2 over 6, which is 1 over 3. C2 is V2 dot W over V2 dot V2. And what is the number here? So it is negative 1 times negative 1 plus 1 times 2 plus 1 times 1 over negative 1 squared, 1 squared, 1 squared. So here I have 1, 2, 1, 4 over 3. That's C2. And C3 is V3 dot W over V3 dot V3. So this formula works for all orthogonal bases. 3 times negative 1 plus 0 times 2 plus 3 times 1. and 3 squared plus 0 squared plus 3 squared. And well, this cancels that. You have 0 over 18, which is 0. So we found the coefficients. And remember, when you have the coefficients of the unique linear combinations of set vectors of a basis, if you put them in a vector form, we call it the coordinate of that vector with respect to that basis. So in this case, C1 needs to go there, C2 goes there, C3 goes there, which are 1 over 3, 4 over 3, and 0. And that's what we have. That's very important, and it happens when we have an orthogonal basis. Finding coefficients and the coordinate is just like piece of